Hi, and welcome back to one last video reviewing the main topics covered in this course. So we'll just recap each topic lecture by lecture, starting with lecture 1. In this lecture on visualization, we talked about how sketching and solid modeling are both important parts of the engineering design process, where sketching is good more so for brainstorming and quick idea generation, and solid modeling is crucial in detailed design documentation. We also talked about the various classes of projection that can be used to represent three-dimensional objects in 2 dimensions on paper or on a screen, like perspective projections, which give realistic pictorial visualizations of an object, the way we see in real life, and a variety of parallel projections, from oblique pictorials to axonometric pictorials to multi-view projections. In this lecture, we focused mainly on isometric pictorials. The main projection class we see was solid modeling and engineering drawings, because this type of projection gives us a 3-dimensional view of an object where the height, width, and depth proportions are all preserved thanks to the equal foreshortening of all axes. Now, this is especially helpful for providing a clear depiction of an object, but we have seen that when it comes to including details like dimensions, multi-view projections are the way to go, as seen by this example. This combination of multi-views with the isometric for clarity provides a complete and clear description of the object geometry, which is necessary to ensure that it is manufactured as intended. We discussed multi-view projections in further detail in Lecture 1b, including how to generate them using the glass box theory, where you place a part within a box, project the views of the object onto the faces of the box, and then unfold the box to obtain the multi-view representation. This is specifically third angle projection, which is used in North America, in contrast to first angle projection, which is used in places like Asia and Europe. So with this glass box theory, we end up with 6 principal views when we unfold the box: the top and bottom views that give the width and depth information, the front and rear views that give the height and width information, and the right and left views that give the height and depth information. Since these views share information, we often just use 3 standard views of front, top, and right, although sometimes more or fewer views is appropriate. Recall that we also include hidden lines and center lines in multi-views, with the line precedence being visible lines, then hidden lines, then center lines, in the event that they overlap. Hidden lines aren't typically included in isometric drawings because it would make them overly cluttered, but in the 2D multi-view drawings, we are able to include hidden and center lines to make it easier to interpret the overall geometry of the part. In this lecture, we also learned about view selection for multi-view drawings. When it comes to selecting a front view, we want to pick a view that best describes the overall shape and/or function of the object. In addition, we usually want to pick the object's longest principal dimension, appearing as the horizontal dimension in the front view. And other considerations include choosing the view with fewer hidden lines and considering the resulting arrangement of the top and right side views. As we mentioned before, these 3 standard views, front, top, and right, are typically included in multi-view drawings to give a complete, unambiguous representation of the object, but generally the rule is to include as many views as needed to fully describe the object's features and no more. In the case of simple parts like washers, bolts, and so on, only 1 or 2 views may be required, but in cases of objects with more complex geometries, like inclined or oblique surfaces or internal features, additional views may be required, and we talked about these in Lecture 2a. This includes the primary auxiliary view for showing inclined surfaces in true size and shape. We talked about adding an additional plane to our glass box, parallel to the inclined surface, and hinging that plane off of one of the principal planes to generate the auxiliary view. We also introduced section views used to clearly depict parts containing internal features, where a cutting plane is drawn on one of the standard views indicating the section viewing direction, and then the corresponding section view shows the view from the cutting plane where the cut material is cross-hatched and the internal features are exposed. So with the isometric pictorials, standard views, auxiliary views, and section views, we covered the majority of views that you'd see in engineering drawings, which were the topic of Lecture 2b. We learned that engineering drawings, aka detail drawings or part drawings, contain all the information needed to fabricate a single part to the required specifications, which makes it one of the most valuable tools in the design and manufacturing process. In addition to standard views, engineering drawings include dimensions, a title block, and other important information like revisions, material designations, and other notes. So we already covered view selection, and this lecture focused mainly on dimensions. We covered 10 main dimensioning rules, which have been summarized in this slide. I've highlighted 3 key dimensioning rules or heuristics for this review. The first one being the contour rule that tells us to place dimensions on the view that best displays a feature. Another good dimensioning strategy is to align or group dimensions with smaller dimensions nearest the object to keep everything neat and tidy. And we also talked about 2 different dimensioning strategies, chain dimensioning and baseline dimensioning, which can also help with dimension alignment. Finally, an important dimensioning rule is to dimension everything, but not to over-dimension, because we want to fully define a part's geometry without providing too much information that it becomes cluttered or difficult to interpret. Lastly, we went over important symbol and hole notations for engineering drawings as shown on this slide, which gives us all the information we need to both interpret engineering drawings and make our own. In the midst of learning all this, we also learned about part modeling and creating engineering drawings in Inventor in the lab lessons, which allowed us to apply our knowledge of interpreting engineering drawings and making our own as well. When it comes to parametric solid modeling in Inventor, the key thing to remember is that every parametric solid model is essentially a collection of features, which are characteristic elements or geometries of an object. So when you approach solid modeling of an object, it is important to first break down the object into a set of features that can be modeled one at a time. As has been said previously, there is no single right way to model a part. There are always multiple strategies that we can take to arrive at the same final part. Once a modeling strategy is determined though, we can execute it by creating a new part file, making sure we choose a template file in the correct units, and then creating our part one feature at a time. Making these features involves creating a 2D sketch on some plane, fully constraining that sketch using dimensions and geometric constraints, and then bringing it into 3 dimensions using one of the 3D modeling tools at our disposal. This slide summarizes the main 3D modeling tools covered in Labs 1B and 2A. The Create tools that bring one or more 2D sketches into 3 dimensions, the Modify tools that modify 3D features, and the Pattern tools that allow us to repeat 3D features in a specific pattern on a part. We walked through the use of these tools in numerous examples, such as the ones shown on this slide. We also covered how to create engineering drawings of these same parts in Inventor, beginning with opening a new drawing file template, and then placing the views using the Base button on the Place Views tab. Next, we learned about adding annotations to drawings, including dimensions, text annotations, center lines, and center marks, using these outline tools in the Annotate toolbar. So that recaps much of the part modeling and engineering drawing content that we covered in the course. The next topic that we transitioned to was mechanisms, which gave a nice segue between part modeling and assembly modeling. In general, we learned that mechanisms are designed to create a mechanical advantage and/or transfer mechanical action. We covered 3 main mechanisms: cams, which transform a uniform rotation to non-uniform linear motion or rotation; linkages, which can produce complex motion based on the geometries of and connections between linkages. We didn't go too in-depth on this beyond computing degrees of freedom using Grubler's equation for 2D planar analysis. And finally, we discussed gears, which are rotating machines with cut teeth that behave as levers, imparting a force on the teeth of another meshed gear. We learned that gears can be used to change the speed of rotational motion, create a mechanical advantage, like increasing torque, and/or change the direction of rotation. We focused mainly on gears in this lecture and the next, but recall that each of these types of mechanisms are related back to the lever, so if we understand levers and torque, we can understand many mechanisms. With gears specifically, we use the fundamental law of gearing to derive these gear ratio equations based on the fact that at the point of contact between 2 meshing gears in a gear set, the teeth of both gears in the gear set must be moving at the same linear speed, and the contact force on each gear must be the same too, according to Newton's third law. We went through a number of gear design examples using the gear ratio, as well as the equation D equals M times Z, relating the gear diameter to the number of teeth via the module. Other guidelines that we must keep in mind throughout the design process is that we can't have fractional teeth on a gear. The module of both the gear and the pinion in a gear set must be equal for them to mesh properly. And out of the 3 main design variables of gear diameter, module, and number of teeth, we can only specify 2, and the third is automatically set via the equation D equals M times Z. We looked at gear train mechanisms made up of multiple gears meshed in series, as seen in the top diagram, where the intermediate idler gears don't have any impact on the overall gear ratio between the input and output gear, but they do serve to change the direction and transfer motion across a greater distance. We also looked at compound gear design, where multiple gears are mounted axially on a common shaft, with the output of one gear set connected axially with the input of the next, as shown in the bottom diagram, which allows for larger speed and torque manipulation in a gear train under set spatial constraints. With compound gear design, the overall gear ratio will be the product of all the individual gear set ratios, as shown on this slide, where the individual gear set ratios are written using the number of teeth. The reason that it's suggested to use the number of teeth in gear train design is so that it can be ensured that all gear teeth are whole numbers. Remember that D and Z are related via the module, so if we design our gear train using diameters, we are automatically specifying the number of teeth as well, and we risk having these be fractional values. For this reason, a strong recommendation for gear train design is to set a module and then go ahead and design the gear train based on the number of teeth, so that you can ensure all your gears have a whole number of teeth, and then you can calculate your gear diameters according to the formula D equals M times Z. We also discussed the selection of an appropriate module. While a smaller module gives more precision in adjusting the gear ratio for a given diameter, it results in smaller, finer teeth that might not mesh well if they are too small. For this reason, you need to strike a balance when selecting a module, which will likely be based on considerations such as the minimum number of teeth and general gear size requirements. Now, we focus mainly on spur gears in these lectures, but the same general design principles apply to bevel and helical gears, as well as worm and worm gears. We also introduced the rack and pinion as another gear type to transform rotational motion to linear motion instead. So the first step in gear train design is most often to determine the appropriate gear type for the application in question, followed by determining the gear train configuration in terms of the number and arrangement of gears, and then setting gear design parameters according to the formulae that we saw on the previous slides. We also covered gear design in Inventor using Inventor's design accelerator. We used the spur gear component generator to model spur gears in assembly modeling based on gear design parameters like module, number of teeth, and face width. Remember that if you get a pop-up message saying calculation indicates design failure, that is because Inventor performs loading calculations for the gears, which we have ignored for the purposes of this course, so it's fine to accept this message. Other than that, Inventor makes it pretty easy to model spur gears with the design accelerator, and we learned that we can incorporate these gears into larger assembly models. It was in Lecture 4A that we talked about assemblies and assembly modelings, where we defined dimensional or geometric relationships between instances of components to create a more complex device or structure consisting of multiple parts. Remember that very few devices are made up of single parts. Instead, many products consist of multiple components that must be assembled together. And that's what assemblies are. Assemblies are a collection of parts or subassemblies that are put together to make a fully functional device. Similar to how we learned about sketch degrees of freedom in part modeling, we talked about 3D part degrees of freedom, noting that each component instance placed into an assembly has 3 rotation and 3 translation degrees of freedom to begin with. In assembly modeling, our goal is to constrain these degrees of freedom, starting by grounding a base component instance and then defining geometric relationships of other instances relative to that. The assembly constraint options that we have in Inventor are shown on this slide. The mate constraint essentially sticks 2 faces together with their normals pointing in opposite directions, and this constraint can also be used to align part axes with each other. The flush constraint aligns 2 surfaces so that they resemble one continuous surface, and the angle constraint allows us to specify an angle between 2 faces. We also have the tangent constraint to make the curved or planar face of one part tangent to that of another. And finally, there's the insert constraint, which is really just a combination of the axis-axis and face-face mate constraints that is especially handy when inserting a bolt, pin, or screw into a hole, and it also gives us the option to lock the rotation of the inserted instance as well. We went through the Inventor assembly modeling steps in Lab 4A, which involves opening an assembly file, placing components, and then applying the assembly constraints presented on the last slide. Also, it's important to remember that an assembly file is linked or associated with the part files of all of its components. So if you want to share an assembly model with someone else, you can't just share the assembly file, you have to share the part files as well. For this reason, the final important step we discussed was saving assemblies using Pack and Go, which zips all of the necessary files together for sharing. In Lecture 4B, we talked about assembly drawings that serve to show how parts fit together and how the assembled device functions as a whole. This includes their main features, such as the assembly pictorial itself, the title block, as well as balloon labels and a parts list or bill of materials that helps to identify all of the components in an assembly and the number of each required. We also covered the 3 types of assembly drawings and their uses, with the outline assembly drawing being the most similar to the multi-view engineering drawings for single parts, where the device is shown in a fully assembled state in a multi-view format as we've seen before, with the optional isometric view for clarity as well. Recall that the outline assembly serves to show the fit and function of all parts in their final configuration. However, in some cases, we may want the assembly drawing to illustrate how a device is put together, and that's where the exploded view comes in. The exploded assembly drawing shows the device in a disassembled state, which may be helpful in seeing all parts of a device in a single isometric view, and it can also elucidate how those parts fit together, which is important information for product manufacture and even for maintenance. The third type of assembly drawing is the sectioned assembly drawing, which shows the device in its final assembled configuration, but with sectioning to reveal hidden components, which also helps us understand how parts fit together as well. And with all of these assemblies, recall the conventions are to omit hidden lines and dimensions, since this is the type of information that is already provided in individual part drawings. In the corresponding lab, we walk through how to create an exploded assembly drawing in Inventor, which requires opening the assembly in a presentation file and tweaking component positions to create an animation, ending in the desired exploded view. From there, you simply have to make a drawing out of a snapshot view from the presentation, and the rest of drawing preparation is similar to what we covered for engineering drawings, with the addition of adding features like the parts list and balloons. So this wraps up our discussion on assembly drawings, but in the following week, we talked about another application of assembly modeling, which is to create dynamic simulations. More generally, we discussed how solid models can be important for design verification, not only for applications like dynamic simulation, but also for others like computational fluid dynamics for fluid flow and heat transfer analysis, where device geometry is a very important factor. This goes to show that solid models and assemblies can be just as useful for design verification and analysis as they are for visualization and documentation. For this course, though, we focused on the one application of dynamic simulation in Inventor, where we went through the steps of creating a dynamic simulation such as the ones shown on this slide. First and foremost, it is necessary to create a well-constrained assembly for simulation. Since we want the assemblies to be capable of motion during the simulation, this involves the use of motion constraints and/or assembly constraints with limits, depending on the application. Recall that assembly constraints with limits allows defined restricted motion of a component, such as the hinge and pin in the topmost simulation, while the motion constraints define motion ratios between components, such as for the screw mechanism in the bottom right. Once we have a constrained assembly, we can enter the dynamic simulation environment to create a simulation. In some cases, this may require inserting joints that describe the motion relationships between components, such as the rolling cylinder-on-cylinder joints for spur gears in a gear train, and then imposing a motion on a joint to make something happen during our simulation. Once a motion is imposed on a joint, we can run the simulation in Inventor and review output graphs of positions or velocities of our joints from the simulation for design verification. These graphs can also be exported to Excel for further analysis if required. So that wraps up the content covered in this course. In summary, we've covered visualization, part and assembly modeling, working drawings, mechanisms, and design verification, which is quite a lot. So congratulations for making it through all of this graphics content.